So tonight we're going to take one problem and see how all the aspects of discrete math that we've talked about so far fit into that problem. Actually, we're going to start with that tonight and finish it on Thursday, or next class, Wednesday. So you remember the power set problem, right? If we have a set S whose elements are 1 through n, then we know how to make the power set for that, right? How many elements does the power set of S have? S has n, right? And the power set of S has how many? 2 to the n. And so the power set of S is the empty set, the sets containing the singletons, and then the doubletons, and so on, right? The triples and then so it has 2 to the n elements. And we can represent this with what? How could we draw a picture with the power set of S? We've done it before. We've made a Hasse diagram of the power set with what relation did we have? Subset relation, right? So if we look at the power set and use the relation, the subset relation, then we can relate sets to each other by whether they're subsets or not. So let's just look at the power set of the set containing 1, 2, and 3. So the power set for S has the empty set, the set containing 1 and 2 and 3, 1, 2, 1, 3, and 2, 3, and 1, 2, 3. So what is the minimum out of this set? So if this is our set right here, then we have relations between what? The empty set, and that's a subset of what? All the other ones, right? So if we started to write down the subset relation, we would have lots of pairs, right? We already have 8 things here, so we'd already have 8 points. The empty set, the set containing 1, the empty set, the set containing 2. So this is the relation on the power set of S with the subset relationship. So we could write all those points out, which is a lot of them, right? But we know from this, we know that the subset is reflexive, right? A set is always a subset of itself. Is this symmetric? It's not symmetric because the empty set's a subset of the set containing 1, but 1 is not a subset of the empty set, right? So it's not symmetric. How about antisymmetric?
Yeah.
It is antisymmetric because if one set's a subset of another, you can't reverse that subset order unless it was the same set to begin with. Right? So it's antisymmetric. And is it transitive?
Yes.
It's transitive because if I have one set, it's a subset of, like if A is a subset of B and B is a subset of C, then A is a subset of C. That works with subsets. And it's not asymmetric, right? Because asymmetric would have to be irreflexive. So now we know this is a partially ordered set. And what's another way to write partially ordered set?
Poset.
Poset, P-O-S-E-T. So that's an abbreviation of partially ordered set. And when we have a partially ordered set, we can draw a diagram for it, right? So any relation, we can draw a directed graph, but partially ordered sets, we can draw Hasse diagrams. So a directed graph would have lots of arrows in here, right? We'd have arrows from the empty set to all the other sets. From the set containing 1, it would have to go to 1, 2, 1, 3, and 1, 2, 3. The set containing 2 would have to go to 1, 2, 2, 3, and 1, 2, 3. So it would be pretty messy, right? So a Hasse diagram is a nice way to make a graph without having to draw all of the arrows. So a Hasse diagram has to have the elements that aren't subsets of anything else would have to go where?
Very top.
The very top. And ones that are subsets of everything would go on the very bottom. So the one that everything is a subset of is the entire set, and that should make sense because that's how we made our power set in the first place, because it's all the subsets of 1, 2, 3. So then the next level we decided was, before, when we first did this problem, had the 2 element subsets on there. And the next level had the 1 element subset. And the bottom had the empty set. Now how do I draw lines on this?
Disconnect them.
The empty set's a subset of all the things on the next level, right? The set containing 1 is a subset of what?
1 and 2 and 1.
1, 2, and 1, 3. And 2 is in 1, 2, and 2, 3. And 3 is in 1, 3, and 2, 3. And then all these 2 element subsets are subsets of the total set. So the edges that we deleted are the ones that go from the very bottom, the empty set, that go up to the third level, and the 4th level, right? And we also deleted all the ones that go from the 1st level to the 3rd level. So we skipped, what are those ones called? The transitive ones. So the transitive edges we deleted. And we also deleted which ones?
Reflexive.
The reflexive ones, which would have been little loops from each set to itself because they're subsets. Okay, so in this diagram, I could look for upper bounds of things, right? First, like, what's the minimal element?
Empty set.
The empty set is a minimal element, and it's also the minimum because it's just one of them. And what are maximal elements?
The set containing 1, 2, and 3.
1, 2, 3 is maximal, and it's a maximum because there's only one of them. So what is the least upper bound for the empty set and the set containing 1?
The empty sets.
Okay, someone said the empty set. Is that an upper bound for that, for 0 and the set containing 1?
No.
Low.
So it can't be a least upper bound. So it has to be an upper bound and then a minimum of those.
It's 1.
It's 1, right? It's the set containing 1 because the upper bounds for 1 are everything I can get to from there. So it's kind of like this part, right? And the ones for 0 is everything. The empty set has everything as an upper bound. So the overlap of those two would be the upper bounds of the set containing 1 and the empty set. So the least, the minimum out of that graph, so if you just look at that Hasse diagram right there, the minimum of that is the least upper bound. So the set containing 1 is the least upper bound of those two. So what the least upper bound is the smallest set that contains both the empty set and the set containing 1. So that's similar to doing like greatest common factor and least common multiple kind of things. So when we do greatest lower bound and least upper bound, it's very similar to those GCD and LCM. Because you could make a Hasse diagram for divides, right? And find least common multiples and greatest common factors in those diagrams. Okay, so what was another representation for, we used another representation for these sets to make it a little easier to write. Does anybody remember?
Gray codes.
So this looks like the gray code problem that we did, right? So it's really the gray code problem that I was getting at. Okay, so this can be represented with binary strings. So we can go back to our zeros and ones, which was at the beginning of our class, where we could use a 0, meaning that the element is not in the set, and a 1, meaning that the element is in the set. So out of this, our length of the string is 3 because we have 3 elements in our maximum 1. So what we'll do is the top one is represented by 1, 1, 1 because it has all of 1, 2, and 3 in it. So the first bit represents whether 1 is in there, the second bit's for 2, and the third bit's for 3. So we could redraw this entire diagram using binary strings. So at the top, we'd have 1, 1, 1. At the next level, this was 1, 2, 3. So 1, 2. And the next one was 1, 3. And the last one was 2, 3. So I put 1s where those elements are in the set. The next level had 1, and then 2, and then 3. And the bottom level had all zeros. So this is the binary string representation for the power set of S, where S was the set containing 1, 2, and 3. And Van mentioned that this looks like our gray codes problem. How does this look like the gray codes problem?
Because when you go along any edge of the graph from one string, binary string, to another, only one element changes.
That's right. So if we go along any of the edges here, we have a 1-bit change. So one element changes. So if you notice, anywhere I go, I've only changed by one element. So making the Hasse diagram was sort of cutting down that graph from all the possible connections to the ones that just change by 1. So this is a gray code, or it's a graph of a gray code, right? Any edge I follow, so any way to traverse this graph in any direction will give me a bit change of 1 every single time. So solving the, if I was using this graph for the traveling salesman problem, solving the traveling salesman problem would be equivalent to getting a gray code that covers all of them, right? So the Hamilton circuit problem is equal to solving for a path in this. So it's equal to solving the traveling salesman problem, right? And also it's equal to solving for a path that starts and ends in the same vertex and each going from one node to another is a 1-bit change. So that's, I meant to write that that's just the gray code problem. So making a gray code for a 3-bit string. Does anybody remember how we made a gray code before? So one way to do it is just to try things in this graph, right? But you might not necessarily cover all of them unless you were careful. So we did a recursive algorithm to solve for a gray code. So we didn't necessarily do it with the graph. This graph is a picture. But what we did is we listed the vertices in order, and we made a recursion to do that. So what we'll do is we'll look at all the binary strings of length 1. What are those?
0.
0.
0 and 1. That's a gray code because as I go from 0 to 1, I change 1 bit, and when I go back from the bottom to the top, I change by 1 bit. That was easy. That's sort of my basis, right? And then for recursion, what I wanted to do is to go from recursively build a gray code for length n. I would start with n minus 1 and then do a process to it. So we have our basis here. This is like our basis. This is a basis recursive code. So the length is equal to 1. And then we assume we have that. And what we do is we copy it over once, and then we reverse it. And then what do we do? Because we want to go from the 1-bit gray code to the 2-bit gray code.
Just count zeros and ones.
I put zeros where?
On the top and ones in the
On the
bottom.
top one. And I put ones on the bottom one. And we can verify that that's a gray code, right? Because since we copied a gray code, then we know these two are adjacent by 1 bit, right? And we just put the same thing on the front, so they're still adjacent by 1 bit. And then for the second one, we know that since we reversed this, that these didn't even differ in a bit at all. So these are adjacent in 1-bit flip, and they have the same start. And then these two are adjacent because only the first bit's different. So we could make a longer one by taking this one and copying it over and then flipping it, putting zeros in front of the first one and ones in front of the second one. So we can write a rule for that. So the basis is our first gray code, if you just list them, is that. And then our recursive rule would be, so let's just say this is G1, right? Gray code of length 1. So we're trying to define G of n. So we've defined G of 1. So G of n is going to be equal to taking a 0 and putting it in front of G of n minus 1 and making that list, and then following it by a 1 in front of the reverse of Gn minus 1. So we're writing that 0 in front means put a 0 in front of all the elements in that list.
Now that prime means reversed, right?
Yeah, I did mean for that prime to be reversed, so this is the reverse. So it's the same list in the reverse order. The cool thing is you can also draw the picture for this, draw the picture for the gray code like what we did for the 3-element, the length 3 gray code. You can draw this picture. You can make a recursive rule for drawing the picture too, which is really neat. So let's look at that. So you have to do the same thing. You draw, first you have to have a basis graph, which we'll do 0, 1. That's a graph where the edges are between adjacent things, where adjacent means you're differ in 1 bit. So just like copying over for the list, we'll do the same thing. We'll copy the graph twice. Let's see, how do I want to do this? So what I do is I copy the graph twice, and then I draw lines in between the very same vertex. So if you don't look at the first bits, those are the same vertices, right? So I draw lines between them, and I put a 0 in front of one and a 1 in front of the other one. So this doesn't give me a list, this gives me a graph. That's why we didn't have to reverse the second one, because the graph doesn't have to do a sequential order. So it looks a little funny doing it for these 4, right? But if I do this again, so I copy it, draw lines between the ones that are the same, and then put zeros in front of one of them, and ones in front of the other one. That's a graph where everything's adjacent by exactly 1 bit. And with a little bit of imagination, you can see how stretching this goes back to the Hasse diagram. Because here's our minimum, 0, 0, 0, and here's our max at 1, 1, 1. If I stretch this out, then this becomes the level right below the 1, 1, 1, and this becomes the level right above 0, 0, 0. Isn't that neat? So you can keep doing this. So you repeat, basically you double the graph, and you draw lines between the same nodes, and then you put zeros in front of half of them and ones in front of the other half. When you do this, this makes an n cube, what's called an n cube. Because this is a 3-dimensional cube, right? So when you keep doing this, however many bits you have in your string, it makes an n cube. That's what it's called. So we could prove that the way we've drawn this, that all the edges are between vertices that differ in exactly 1 bit. How would you prove it? By induction, right? Anytime we have a recursive process, what we would want to do is follow the recursive process and show that at every step of the recursion we still had what we wanted. So it would be an induction proof that worked on the recursion. So let's just do it for the list because it's easier for the list. Easier than for the picture. Although for the picture is not too bad either, because it works the same way, right? Because we're copying something over, and if we assume that the nth level has everything adjacent by 1 bit, then copying it over doesn't change anything, and it's just the new connections that we make that we have to prove only differ in 1 bit. So actually, let's do it for the graph, because we did it in class before for the list, right? You guys remember that? A long time ago. With recursion and induction, we did it for the list. So let's do it for the picture. So let's prove that the gray n cube is gray. And gray means that all edges are between strings that differ by 1 bit. Exactly 1 bit, actually. So we're going to prove by induction, and we're going to prove it on the length or on the size of a node, right? The length of the node label. It's on n, so n is the length of the string at each vertex. So our basis should be length equals 1, right? So that graph is just a 0 connected to a 1. And you can see by inspection that this one is gray, right? That edge is between two things that differ in 1 bit because there's only 1 bit, and they're different by 1 bit. So this is gray by inspection. Now what do? We have an assume step, right? So we want to assume that the n cube is gray, and we want to prove that the n plus 1 cube is gray. And whenever we've done a proof, an induction proof from a recursion, what do we do right after we finished writing this basis assume proof? We would start with the recursive definition, right? And then we plugged in things from the assume. So that's exactly what we're going to do here. We're going to use our recursive definition. Although it's not an equation, right? It's a rule. So we need to start with the rule. So we're assuming that the n cube is gray. We're going to prove that the n plus 1 cube is gray. And we want to start with our rule. So to build an n plus 1 cube, we did what? We took two n cubes, right? So whatever the n cube looks like, we take the first n cube. So we copy the second n cube. And then we drew edges where?
The same nodes.
We drew edges to the same nodes, right? So if we have x over here, this will be x over here. So our rule after that, only thing we did after that was change the labels, right? The labels over here all got labeled with a 0 in front, and the labels over there got all labeled with a 1 on the front. So if we want to prove that the n plus 1 cube is gray, we have to show that this is sort of our diagram, okay? This was how we built an n plus 1 cube. So we have to show that the stuff in here is gray, the stuff in there is gray, and then we have to show that all of these edges are gray. So if you draw a good picture, it's easy to see how your proof is going to go, right? That's why we start with a recursive definition. So this is sort of a kind of a fuzzy one, but you guys know what I'm talking about, right? Okay. So here, how do we know that the things in this circle are gray? All the edges in there. Because it's an n cube. It was a gray n cube to begin with. So everything in both of the circles, by induction, by my assume step, is gray, right? So all of these edges on the inside by the assumption, because all n cubes are gray, right? So if it's gray, that means all the edges are between vertices that differ in 1 bit. So now all we have to do is prove those lines in the middle are gray. Any ideas?
Well, if they're the same thing except for that leading number, if If the leading number is the only thing different between the two, then they have to be a gray code between themselves.
Right, does everybody see that? Does everybody see how they're gray? So it seems a little, it's almost trivial to do the proof, but it's by the way we did the problem that made it easy to do the proof. If we did the problem in a different way, it wouldn't be easy to do the proof, right? Okay, so all these edges, so all the new edges are formed by joining 0x to 1x. Right, so those edges are, if I wrote them in an ordered pair format, it would be 0x, 1x. Which differs in exactly the first bit, right? And x is just all of the bit strings of length n. So x is a bit string of length n, length n, and 0x, 1x is gray because these vertices differ only in the first position. Are we done? We're done. We could just say one more sentence, right? We could say, therefore, the entire graph is gray since all the edges are gray. So I'll write that.
So actually, this is actually really valid because per unit, when you reversed it kind of from 0 to 1, because that's valid, then that's why the whole thing is valid.
That's right. If we didn't connect the nodes the way we did, then it wouldn't work. So the way that we built the n plus 1 cube was to make 2 copies of the n cube and stick zeros in front of one copy and ones in front of the other copy. And we only put edges between the nodes that were the same before we put the 0 and 1 on there.
So if you didn't put that criteria in, this proof would not be accurate.
That's right. So if I didn't build the n plus 1 cube that way, this proof would not work. Or else if the basis didn't work, this wouldn't work, right? So if I didn't have a gray code for length 1, then I wouldn't be able to do it. So that's key. Induction proofs need both parts to work. They need the basis to work, and they need the recursive or inductive step to work. So we have to do both parts whenever we do an induction proof.
I guess a wise guy could say, isn't that like cheating? You set the stack.
That's a good point. So some people would look at this and say that's cheating because that's how you built the graph in the first place. But if you were solving this problem and you had to make graphs, make the n plus 1 cube, and someone had just drawn them before and said, oh, here's a graph where all the nodes are adjacent in 1 bit, and they didn't give you a recursive definition and you had to come up with it, then the clever way would be able to say, well, if I wanted to do it by induction, how could I keep increasing the size of the graph and build it so that the parts that I put together are gray and then the connections are gray? So the person who made this up was really clever. So it looks like cheating now, but that's because someone already figured out the hard part, and that was to figure out how to make those graphs in the first place.
Is there any other ways to make those kind of graph? To build the graph? Any other way?
I mean, you could just draw all the binary strings and then connect the ones that are different by 1 bit. So you don't have to do it recursively, right? There's lots of things that you can do that you don't have to do recursively. So it's just that the recursive way, I don't actually have to check everything and make sure that things differ only by 1 bit. I know already, because of the way I made it, that they differ only in 1 bit. And that's the advantage to doing the recursive method, because I already know that big chunks of the work are already done for me just by copying over what I did before. And that's why we do lots of, Java coding now, because people have already done some of the work before, so we don't redo what's been done before. So if you have to generate if you have to generate all the gray codes of lengths from 1 up to 1,000, it makes sense to do it recursively. If you just have to do it once, it might make sense just to draw it. But still, in order to make sure that I was correct, I would try to use something like this, because then I could prove it was correct without having to go through and check everything. So that's one advantage to using recursion, because you know that it can only work one way. If you have a recursive rule, it's either the basis or the recursive step, and there's no other way that the program could have done something. But if you have, say, case statements, like say case 1 do this, case 2 do that, you might have places where you didn't do exactly the same thing, right? You didn't use the same process to do something. So you can't use one little proof to prove the whole thing if you do each step differently. So that's one of the nice things about recursion, is that it sort of condenses down the work that you have to do if you want to prove something's correct. And it also reduces the amount of work you have to do, because you're doing incremental work, right? So if you have to do lots of things, if you have to fill in a table, say, of all of the values for a function, if you can define it recursively, you do less work at each step, right? Remember, n factorial is a classic recursion, right? Which is what?
N times n minus 1 times n.
N
N minus 1 factorial times n is a recursive definition for that. And I have to give what as the basis? 1 factorial equals 1. So if I had to fill in a table of all the factorial values, I don't want to calculate factorial all the time, right? Even if I have a calculator, you run out of digits pretty soon. So I would want to use this recursion to fill in a table like that. Or anytime if I need a lot of values and I know a recursive definition, I want to use the recursion. Same thing for the ones where we had if we had this kind of format, I would definitely want to use a table and a recursion for that instead of using a closed form, which is going to be a quadratic, right? So you have only table lookups. If you have enough memory, you only have table lookups and addition and multiplication to do if you're going to do recursion. If you're not, you're going to have to do squaring every single time, because this does quadratic. What is the characteristic equation for this, by the way? If I want to solve this recursion for closed form,
C sub 1.
this is x squared equals 2x plus 3, right? Characteristic equation. If it goes back 2, then you know this one's going to be x squared, the next one will be x, the next one will be nothing. 1, right? Leave the coefficients there. Solve for 0, and then you would find the x, right? So I'd find x1 and x2, and then my recursion would be c1 x1 to the n plus c2 x2 to the n, assuming that x1's not equal to x2, right?
Which is not.
And they're not in this case. I don't know what they are in this case, because they're
Negative 3 and positive 1.
negative 3 and positive 1. That's good.
I'm sorry, x minus 3 and
3
x
and
plus 1, so it's actually 3 and negative 1.
It's really cool that I made a factorable one without thinking about it. So this would be and how would I figure out C1 and C2? Because I know that some of you sometimes, you'll get this far on a problem and you'll forget how to find C1 and C2, right? How do you find them? We have 2 unknowns, so we need 2 equations.
And you know s of 0 and you know s of 1.
So I know 2 values for s.
And with those, you know the value of n for
Right.
the equations.
So I know s of 0 is 1. So that's going to be
3 to the 0.
C1 times 3 to the 0, which is 1, plus C2. And then S of 1 equals 5 is going to be 3C1 minus C2. So then you would solve those, and then you could plug back into Sn.
Yeah, just adding the 2 instead of canceling out the C2s.
Yeah, I'm not going to finish solving this. I just wanted to remind you how to find closed form for this one. So you'll do this again in another class. So the problem we've been working on before this was the power sets and binary gray codes, right? So our all-encompassing problem was the power sets and gray code problem, which ended up being the same thing. Right? So that problem, we've already shown that it has sets in there. It uses a lot of set properties, you know, subset and that sort of thing, definitions of sets. We could also define it recursively, making the graph for it. And we could prove by induction that it was gray. It also represents some of the problems in graph theory, right? Because we could look for the Hamilton circuit, and we were drawing graphs in the first place. It also represents binary relations, because our graph in the first place was a relation diagram. It was a directed graph that we had reduced to a Hasse diagram. So this was one that was reflexive, anti-symmetric, and transitive, which made it a partially ordered set, so we could draw a Hasse diagram for it. So there's only a couple of things that we've done in this class that we haven't done yet with this problem.
Predicate calculus.
What's that?
Predicate calculus.
We didn't do any predicate calculus, but hidden in that reflexive and anti-symmetric and transitive was predicate calculus, right? So that stuff was in there. We just didn't have to use it because we've done that problem so many times. So if you go back to those definitions, all of them are in predicate calculus.
Counting.
So there's counting. There was a little bit of counting that we did so far, right? The number of nodes that we had was 2 to the power n, where n was the size of the original set S, right? So we can look at some more counting in this, because there is more counting. And the other things that we didn't do is we didn't use propositional logic very much. We used it a little bit to convert our set notation into a binary string notation. We'll do some more counting in a minute. And the only thing left that we didn't have in there is big O. And growth of functions. What we're going to do today is we're going to look at some of the counting problems that are embedded in the same problem. And next time, if I can, I'll come up with some big O applications in it, which I think there are. And I'm also going to do a circuit design problem with it, so that we'll have everything is all in one problem. It's kind of neat. So you'll remember all the subjects that we've done in this class. Then they're all related by one problem. So if we go back to let's just go back to the strings in the Hasse diagram, because that's the nicest way to look at these. By the way, another name for this particular graph is also called a lattice. A lattice is when you have a partially ordered set pretty much that has a minimum and a maximum. A lattice is when you have every single pair of elements has a least upper bound and a greatest lower bound. So they have a minimum and a max, like sort of every pair. This is known as being well ordered. This is almost well ordered. It's not quite well ordered. It's almost. Right? Because the reason why it's not well ordered is if I can compare any two things and tell which one is bigger or sort of higher up in the chain. But we have things that aren't comparable, right? Which things are not comparable?
The 1 0 0 0 1 0 and 0 0 1.
The ones on the same level are not comparable, right? I can't put them in any order. But I can put all the other ones in an order. Like all the pairs, I can put them in order, except for the ones on the same level. So this is almost well ordered. So numbers, regular numbers are well ordered. Because every single pair, I can pick which one's bigger. Okay, now let's suppose that I made a much bigger lattice than this. Like each node has n digits. How am I going to know how many things should be on each level of the lattice?
You can use Pascal's triangle.
I could use Pascal's triangle. Let's hold off on using the triangle right quick. How could I know, using some kind of counting formula, how many things should go on each level?
It's either a permutation or combination. You have a number, and some of them are ones. So it's
Right, well,
I've got
on the
three
bottom
choose.
level, how many of your digits are 0?
3.
All of them, right? On the second level, how many digits are ones?
One.
Exactly 1. On the next level, how many are ones?
2.
2. On the next level, how many are ones?
3.
So if I had a lattice with length n, what do you think? How many things, like the bottom level should be all zeros, right? The next level should be all the strings with exactly 1 1 in them. The next level should be all the strings with exactly 2 1s, right? So out of these digits, I just have to choose which ones get to be 1s in each level. So in this level, how many get to be 1s? None of them, right? In the next level, out of 3 of them, I have to choose 1 that gets to be a 1. On the next level, out of 3 of them, I have to choose how many that get to be 1.
2.
2.
And on the last level, all 3 of them get to be 1s. So in a Hasse diagram for the power set for n elements, this would be Cn, choose whatever level I'm on, right? So if I'm on the 0th level, I choose 0 of them to be 1s. On the next level, I choose 1 to be 1s. On the next level, I choose 2 to be 1s. And on the last level, I choose all of them, so on and so forth, up to the nth one. So it would be Cn0, Cn1, Cn2, all the way up to Cnn would be the top level. Now let's just think about one node here. This one's adjacent to 2 on the next level, right? If it had n bits and one of them was a 1, and this had n bits and 2 of them were 1s, how many edges should I get? So let's make an example. Let's do 5. Okay, so here's one on the 1 level. Which ones will it be adjacent to on the next level?
10001.
10010.
So 1001, 10010. What else?
10100. And 11000.
So that's 4. How could I have done that with the counting formula? I have to add 1, 1, right? So out of the digits left, one of them has to be a 1. So out of 4 digits, I have to choose one of them. So C41 should come out to be 4 at this case, right? So what is the formula for C41? It's 4 factorial over 4 minus 1 factorial times 1 factorial. That's 4 factorial over 3 factorial times 1, because 1 factorial is just 1, right? And that should be 1. Sorry, that should be 4, which is what we got. So now we know the number of edges between any 2 consecutive levels, right? It's however many zeros are left, choose 1. So if we look back at this graph, in between these 2 levels, I had 3 zeros, so the number of edges from one node to the next level should be 3, because it's C3, choose 1, right? And that makes sense. I've got 3 here. There's exactly 3 things I could have an edge to from here. And then here, there were 2 going up, because there were 2 zeros left, and I just had to choose which one of them was going to be a 1. In the last case, I only have 1 zero left, so there's only 1 edge going from each. Isn't that neat, how there's counting problems all through the whole thing? So if you were writing a program to do this, you could double check. Or you could even actually say from 1 up to combinations of n things taking this many things at a time, put an edge here, here, here. Right? So for each node, you could say, okay, now I have to make an edge that goes to the one that has a 1 in this position. Now I have to make an edge that goes to the one that has a 1 in that position. And you could do it for all the positions.
So 010 and 101 should not actually be connected then.
010 and 101? No, that was an accident. So it should have exactly 2, right? That's a good way to check, see? That's another instance of me making mistakes for y'all to find, right? Yeah, right, Tim. So in the first place, we could count how many nodes we have in the first place by knowing how many binary strings there are of length n, because it's 2 to the power of however many bits I have. Then I can count how many are in each level, and I can count how many edges are from one level, from one node to the next level. And another interesting thing to note about that is that all these sums of factorials end up being a power. Right? So the number of nodes we had on each level, right, we had on the bottom level, so let's say on the top we had CNN. On the next level we had CNN minus 1. On the next level we had CNN minus 2. And then on down we got to CN2, CN1, and CN0. That was our total number of nodes, right? And then we already knew that adding all of these has to come out to the total number of binary strings of length n, right? So that's another interesting formula that mathematicians do stuff with. I'm not really going to do anything with it now. I just wanted to point out to you that all these factorials added up to give you a power of 2.
And there are 2 to the n.
Nodes.
No.
This is the number of nodes on each level, right? Each one of these numbers. On the 0 level, I have 1 node because n choose 0 is just 1, right? This is the number of, these are the number of nodes on each level. So the total number of the nodes in the nodes in the graph has to be 2 to the n because that's how many nodes I had to begin with. And we also know this is symmetric, right? So the number of nodes on the bottom level is the same as the number of nodes on the top. Right? So this is 1 here and this is 1 there. How many is on the next level, on the first level?
3.
See, n choose 1 is n, right?
Right.
The next level is n choose 2 is n factorial over n minus 2 times 2 factorial, right? Sorry, n minus 2 factorial. So this is n times n minus 1 over 2. So, and they go on and they're symmetric as you go. So if this is symmetric, then sort of across the halfway mark, I have the same thing. So how do I know when I have a halfway mark or if there's something in the middle that doesn't get mirrored?
If n is odd or even.
Right, so it depends on whether n is odd or even, right? So if n is 1, I have just 2 levels, right?
Right.
If it's 2, then I have 0, 0. And then the symmetry is about there, and the middle one has 2. So usually if you're going to solve a problem, like if you want to solve something for all the lattices, you would probably do it for the even ones and for the odd ones because they're slightly different, right? So all the odd ones look the same and all the even ones look the same. So you'd probably solve the problem for, if you had some kind of problem with lattices, you would do it odd ones and even ones, separate one.
Where were you going with the argument that there's one node at the bottom, one node at the top, hence symmetric? Were you going to add to that?
I wasn't going anywhere with it except for pointing out, remembering that these formulas make these happen like this. So in the picture, we can remember that those are the same, right? If we go back and look at the diagram of a lattice, let's look at this one. The number of nodes in this level is the same as the number of nodes in that level. The reason for that is on this level I have to choose, out of 3 I have to choose 1 bit to be a 1. Right? Out of these I have to choose 2 bits to be 1s. But that's sort of a symmetric thing. Right? Choosing 2 of the bits to be 1s is exactly the same as choosing 1 bit to be a 0. Right? And that comes from our counting formula. Right? So if we look back at our factorial formula, I was just reminding you that the factorial formula makes it so these things are symmetric. So if I take n things and choose k of them, that's the same as choosing sort of the complement set. Everybody remember what a complement is? Complement is everything that wasn't in the original one. So that was because of our formulas. If we do n factorial over n minus k factorial, this formula over here is n factorial over k factorial times n minus k factorial. And since, what is the property that multiplication has that makes this equality true?
Commutative.
It's commutative, right? So since the order doesn't matter, what order I do this multiplication, then these things are equal. So that was the point of pointing that out to you. Also, it's cool that, the diagram grows. Like, it starts like this, and it goes out, and then it gets straight, and then it goes back in again. So mostly it grows a lot until it gets to the middle, and then it goes back. Are there any questions? Okay, so the last thing I'm going to do is just write down the description of this problem so you'll have it like in one spot, since I didn't do it right at the beginning. So this is our universal discrete math problem. And no one else is going to call it this, it's just me. Okay? That's right, Tiffany's universal discrete math problem. Let's say the binary So this universal problem was the binary representation for the subset relation on the power set of S, where S is the set of elements 1 up to n. So each set is represented by a binary string. Zero if the element's there is not there, and 1 if it's there. So, and just to remind you what things it represented, we had sets, binary relations, recursion, induction, counting, graphs, and the traveling salesman problem.
You didn't get into big O. And,
That's right. That's what I said. We'll save for next time.
okay.
And just a teeny bit of logic, right? So that's it for today. And next time we're going to talk about big O and logic circuits.